All right, in this video, we're going to talk about how we build these confidence intervals, but with a normal distribution. So to kind of reiterate, in the last video, I mentioned, how we can build these confidence intervals, and I have this written out here as well, but in a different way. But the interval essentially is going to be consisting of the sample mean, and that's usually in the middle, and then we subtract and add an error to determine the overall interval. Um, this error, now we have a formula. The error is equal to z star, which we'll talk about in a minute, times sigma, our population standard deviation, divided by the square root of our sample size. And sample size is usually n. So that'll be our error formula. What is this z star? That's my next part right here. So z star is the critical values of z. Okay, well, what's a critical value? A critical value is a line on a graph that splits that graph into sections. And I have a couple examples right down here. So for example, right here, this is an 80% confidence interval. And essentially what they did is about 80% of the area, or 0.80 of the area, is right here in the green. And then the rest of the area under the curve, which would be about 0.2, is here in the pink, right? So this is an 80% confidence interval. And these are the z values that are associated with an 80% confidence interval. Here's a 90% confidence interval. And you can see that the area on the sides here kind of got smaller. And the area in the middle here, this got a little bit bigger. So this is going to result in a bigger interval. When we have a 90% confidence interval, it's a bigger interval. Because we're saying of all the samples that we take, we think that 90% of those samples will contain the true population mean. Down here we have the 95% interval. Again, we're kind of moving out further. We have a smaller area on the tails here, in the tails. And then we have the z values of 1.96, positive and negative. That means 95% of the area is in this green shaded piece right here. And then last but not least, we could have a 99% confidence interval, where 99% of the area, 0.99 of the area is right here in green, and we have the tails are really small at this point on the edges. So the lower the percent, the smaller the interval. And as we increase our percentages, we get a larger interval, which, kind of makes sense. If we have a 99% confidence interval, that we're saying that of all the samples, 99% of those contain 99% of the interval, the confidence intervals for those samples contain the true population mean, whereas 1% does not. And with a 99% confidence interval, it's a bigger interval. There's a lot more values. So yeah, it is more likely that we will capture the population mean in one of those intervals. Whereas the smaller the interval, right, the less likely it is that we are going to capture that population mean. Okay, now let's actually construct a confidence interval for one specific sample. So this first example, I just have it all typed out, and we're just going to talk through it, and then we will work through one together. So we have a random sample of 100 car engines. I'm going to go ahead and just write out n is equal to 100 a mean weight of 425 pounds. So the sample has the mean weight of 425. So that's the sample mean, X bar. We're going to construct an 80% confidence interval for the population mean if the standard deviation of the population is 900. Okay. So there's a few steps we got to take to complete this problem. But fortunately for all these problems, the steps are the same, right? So you just kind of have to repeat the process for every problem that you do. So the first thing you want to do is find the critical values. And so if we have an 80% confidence interval, we have to find the z-values that correspond to this confidence interval, which means the z-values such that the area between them is 0.80. So we've been working with z-tables, right? Z-tables give the area to the left of a z-value, and essentially we're kind of working backwards. They're giving us the area. We know the area is 0.8, and we have to find the z-values that correspond to that. Now, the good news is we are not going to go through that entire process. You are going to be provided a list of critical z-values because, first, it's just a little bit easier, but a lot of times with these problems, we use the same confidence intervals over and over, right? We might use an 80% over and over, an 85%, a 90%. And you don't want to have to go through the process every single time of figuring out what those z-values are. So you're going to be given a table of those z-values. Yay! But what I was explaining about up here, I just wanted you to know where the z-values are coming from. There is a way to figure it out. If we have an 80% confidence interval, there's 0.8 area. The area between those z-values is 0.8. If we have a 99% confidence interval, the area between those z-values is 0.99. But once again, it'll be given to you. So for this problem, we have a 0.8 confidence interval, 80%. If you write 80% as a decimal, 0.80, right? It's 80 divided by 100. And that's how you can convert from the percent to the decimal. So our critical z-value is 1.28. So that's going to be our z star in our error formula. So we've already figured out that piece. And we don't have to do much calculation for that. You just look it up in the table. Just make sure you're looking at the right confidence interval. Now, once you have your critical value, your z star, we're going to go ahead and plug that in and figure out our error. Okay. Just so you know, we take the positive z-value, not the negative. So all your critical values are going to be positive. Okay, so plugging in our information, our critical value is 1.28. Our standard deviation was 900, and then the bottom here is the square root of the sample size, so we have the square root of 100. Simplifying, we end up with an error of 115.2. So the last step, right? So you just had to figure out your z-value, your critical z-value, or your z star, and plug it into your formula with the other information you need. And then the last step is to actually figure out the bounds, the lower bound and the upper bound for your interval. And to do the lower bound, you take your sample mean, which was 425, that was stated in the problem, and then subtract the error. So we have 309.8. And then the upper bound, same thing, same sample mean, 425, but now we're adding that error, 540.2. So our confidence interval for this sample is 309.8 to 540.2. So now we have an interval, a range of values that we believe there's an 80% chance that this interval contains the true population mean. So, and I have that written out here in two different ways because in the first video and earlier in this video, one way to think about this is if you take all possible samples. If you have an 80% confidence interval, then we believe that 80% of the confidence intervals for those samples will actually contain that true mean. But another way to look at it is, since we only did, an interval for one sample, this is just an interval for one of those samples. We didn't find the intervals for all of them. With an 80% confidence interval, we believe there's an 80% chance that the true population mean actually lives within this interval. So there's two different ways to think about it. You can think about it as, looking at all of the samples, 80% of all the samples will contain that true mean, or if you're looking at an individual sample, we believe that, there's an 80% chance that interval contains the true mean.